I've been passionate about ecological sustainability since I was a little kid, and I've been particularly passionate about sustainable building and sustainable business since at least 27 years ago when I opened up my own company, um, Remains. And it was about 13 years ago when I needed to expand my manufacturing space, and I was lucky enough to buy this old factory that's on the screen there. And I was able to take this whole bucket of ideas of sustainability sort of measures that I wanted to put into effect into this building. I had visions of like windmills running on the roof and gardens and water recycling and many other things. And a lot of that stuff did end up in the project. But what I was struck with through the renovation process was the sort of perverse incentives that lined up in what seemed to me unsustainable directions, like where I was interested in putting in ceiling fans and awnings. The prevailing sustainability framework was pushing me to put in a high efficiency air conditioning system. Where I wanted to put in a clothesline, they were saying, well, put in a, again, efficient clothes dryer. And it seemed like there was a lack of understanding of the truly sustainable benefits of the toolkit of traditional building, of doing with less, of doing things more simply, things that were suggested by, there was eventually that turned into a LEED Gold project. And the LEED framework was, it seemed to push towards more complicated solutions and more technologically driven solutions. And that, it struck me that the sort of mainstream conversation about sustainability lacked a real straightforward language to talk about the value of non-commodifiable solutions, of doing things simpler or doing without. And this panel discussion, hopefully, with my three colleagues here, will help illuminate the benefits of traditional architecture in terms of sustainability. Now, I'm up here at this podium because a little over 10 years ago, when I got involved with the ICAA, one of the things that seemed most salient to me about this revival of interest in traditional building was the fundamentally sustainable nature of traditional building. That what we were talking about was a mode of building that prioritized simple solutions, durable solutions, solutions that were adaptable over long periods of time, and solutions that were in tune with local climate and the local style and local culture. Now, the ICAA has always offered many cultural and educational programs that highlight specifically and strongly sustainable things. Like we'll have programs about materials, we'll have programs about structure, we'll have programs about town planning. But until this conference, now it seems like we infrequently gathered them under one roof and made the headline sustainability. So it's one of the biggest reasons that I'm excited to be up here, in spite of my, again, deadly fear of public speaking. And that illumination of the real profoundly sustainable nature of traditional building strikes me as the widest bridge to the new generation of students and emerging practitioners. But not only as an opening for traditional building or speaking of traditional building to the upcoming generation, but also to the current group of practitioners and their clients, architects and builders. I think we need to make the value of traditional building in terms of sustainability manifest to those folks as well. So the theme of this conversation, redefining and measuring sustainability in the lens of traditional architecture, will hopefully let us answer questions like, how can we do without an air conditioning system, rather than what is the most efficient air conditioning system? And I threw together a couple of slides of projects that I thought They, on a very basic and gut level, they illustrate to me what is sustainability in traditional building, like that house in Baton Rouge on the left, or that school in Senegal on the right, or these houses in Iran that take advantage of either wind pulling cool air through a low level of water, or catching breezes in those elevated towers, or in projects as diverse as this community center in China on the left, or that housing development in Spain on the right. And the panelists will hopefully be able to tell us a little bit about why those projects are truly sustainable, and how you go about measuring it. Like, what can we say in concrete terms to the rest of the world about traditional building that makes it more than just a gut feeling? So it's with great pleasure that I want to introduce to you Steve Mouzan in the center here, who is an architect and an urbanist and the founder of the Urban Guild, and also the author of one of the seminal books about the intersection of traditional building and sustainability, called help me out, Steve, The Original Green. Thank you. And John Onyango on the end, professor of architecture at Notre Dame and also a practicing architect, and Patricia Ondrasik, also a practicing architect and professor of sustainability at Catholic University. And I'll let all of them introduce themselves a little more fulsomely when they're up here, as they know better than I how to do that. I also want to thank very much the Institute of Classical Architecture, the staff, and the volunteers and the board who put this conference together. I know that it's been at least 4 years in the making. To my staff, especially Leanne Latch in the front row, who's helped me work on this presentation, and the folks back in my office who did the technical work, and to the fellows of the ICA who've been supporting me in this sustainability initiative also over the past about 4 years. So with no further ado, I'd like to invite Steve up to the podium.
And if you want to submit some questions, just scan the QR code there, and we're going to make this about half presentation and half discussion. So hopefully there'll be a lot more time than normal for discussions. The idea of the original green actually it's about 15 years ago. I was talking to some folks at what was at that time, I think it was at that time, it was ICA. There wasn't the second A at the end. And anyhow, Victor Duby, who was at that time the director of education or something like that, I don't know if that's his exact title, he actually commissioned the very first Original Green lecture. It was an all-day event in New York a couple of years before the book came out, and it actually was it was really essential to the book, which came out in 2010. And basically, the Original Green is the sustainability that kept all of our ancestors alive, so that we could actually live today. It was what all our ancestors knew by heart. The basic proposition is that sustainability should be considered to be keeping things going in a healthy way long into an uncertain future. But that raises the question, it's healthy for who? Okay, because if we look at it at an individual level, we should want to surround ourselves with enough armor and so forth that it becomes, that the risk of damage to us individually is less. But of course, that becomes an arms race, as we've seen with the size and weight of vehicles and over the last several years. What we should be doing instead is building healthy communities for everyone in the community, not each individually trying to compete to have bigger, stronger, heavier truck to run over somebody else with. So. But the Original Green is not just low tech. I want the best tech I can get. I want the best computer I can get, the best camera I can get to help me do better work. So by all means do that. But it's not just Gizmo Green either. Now, what Gizmo Green is the proposition that with better equipment, better materials, that's the path to true sustainability. But the problem is that what it really means because they're saying better on all these things. That means you got to buy more stuff, but also because it's better, it's more expensive. So you need to buy more expensive stuff and more of that stuff from us in order to call yourself green. So today, because of that, there's no widespread agreement over what sustainability actually means. If you go to the AIA conference, for example, the steel guys are telling you why they're the most sustainable thing. The glass people are saying the same thing. The timber people are saying the same thing, but those other guys are not. So it's a very much a disagreement. It's also not just historical. I advocate for something that I call a living tradition. And anybody with decent eyesight and a copy of Bannister Fletcher can obviously see that architecture has evolved over time. It's not just been just a replication of some perfect point in time. There is a book by Roger Scruton that everyone here needs to know. It's How to Think Seriously About the Planet. And basically the point he makes is that the more local we think, the better off we are. The most local thing is home. The second most local thing is hometown. There are a number of things that really should be calibrated to the region, but just as soon as you talk about universal standards, then that's, in universal metrics, that's just like deadly poison. Because, if it works great in Cape Cod, it'll be ridiculous on the Gulf Coast and vice versa, and many other places in the world. Okay, so there's three realms of the original green, and that is the places, the buildings, and then the societies that inhabit them. When I wrote the book, I did not understand about the key importance of the societies. It just hadn't crossed my mind. But over the years since, that clearly is an important thing. Original green places have four foundations. They must be nourishable, accessible, serviceable, and securable. This is what I call the web of daily life. And basically, a lot of people call this the 15-minute city. And of course, that started a great conspiracy theory and huge protests and all this. But really, the 15-minute city is just every city built in human history until the internal combustion engine. But the real question is how much can you get to self-propelled is this shows. And then within the societies, that educational strength, economic, cultural, and wellness strength. There is a, you ask, well, how do we do these things in a more natural way? For example, with street trees, they have a great wave of benefits. And so what happens is some of those benefits are economic. Like if there is a street tree anywhere on your block, the value of your house is between $6,000 and $8,000 more than what it would be without any. If there is a street tree in front of your house, that value increase could be somewhere between $15,000 and $20,000. If you just tell the people that, they will all flood Home Depot and Lowe's and go buy their street trees this weekend. So we should be hoping to do things in that way as opposed to something that needs a lot of top-down funding. So let's talk about the buildings. If a building cannot be loved, it will not last. Doesn't matter what the carbon footprint of the building is after its parts have been carted off to the landfill. So it just doesn't matter. There's three sources of lovability: things that reflect us, delight us, and that put us in harmony with the world around us. Things that reflect us, it can be things that reflect literally the human form, the human hand, and the culture of the region. This is the human form, the proportion of the individual parts is in addition to the overall, and of course the standing human form, its verticality or horizontal arrangement. The vertical arrangement of the humans are reflected, of course, in the orders and in even the pedestal and the column and the entablature, and then the human hand, the evidence of the hand at work, and the regional skill sets that go with that, and regional materials, and regional patterns as well, things that delight us. And there's a number of these sensual delight us, things that literally are senses, thermal and sound, and sight, group delight, and there's a number of types of those. Memory delight is something that if all you have is a suite number or street address to say something really important happened to me here, that diminishes the memory. Intellectual delight is the one part that architects actually get right, but it's intellectually within just the profession itself. The sheltering delight, challenging delight can be like a point of embarkation or a high place to view, and then things that put us in harmony, mathematical and so forth. These simplicity, you say, well, that isn't simple. Look at all the textures and colors there, but that's a very simple dish. So it depends on how you look at simplicity. Authenticity, this is a timber column. The cracks give evidence that it's solid. There's harmony with natural processes and with natural laws and natural forms. And then the one that had been quite mysterious for a long time, which is harmony with the region. Here's Beaufort. Here's Pienza, but this looks ridiculous because obviously that something is definitely not harmonious. And you know what? I'm going to zip through these a little bit more quickly because I actually had forgotten that those couple were in there. Okay. When looking at durable buildings, build for the ages, not the cap rate. In other words, if you build a 1,000-year house, Clay Chapman, who built these, that's his username on Twitter. If it lasts for 1,000 years, then the cost is negligible over time. Adaptable buildings. This building has been savings and loan of Banana Republic these days, and many other things over the time in between. Frugality. Let's condition the people first instead of the buildings first, so that when you return indoors, you might be able to just throw the windows open and enjoy the day. And also building smaller and smarter. And then let's put the buildings back to work. Some of the most endearing things about buildings are those things which engage the humans. And how do we make this change? By having great models that are small enough to be able to be perceived easily. Like, for example, Seaside on 60 acres changed so many of the development paradigms in America, and that change is still occurring. Thank you very much.
Good morning. Yeah, so you see how I'm John Onyango, born in Kenya. So I work at University of Notre Dame, work as an architect in Kenya, in the United Kingdom, and also here in the US. I've done some work here as well. Now, my interest in sustainability comes really from my background. I mean, I grew up where we didn't have electricity, and you learn to adapt to the conditions. And I look back, and actually, it isn't bad at all. I mean, your life is determined by nature, the way God determined it. You go to bed when it gets dark, and you wake up when it gets light. You read when you need to read, with light outside. When it gets dark, you go to bed. It's a simple life that you don't need to introduce other things that destroy your life. So what I'm going to talk about today is really some study of some sustainability, how we measure sustainability in different buildings. I'm going to look at one particular building in India, but I've done work in Portugal. I looked at some buildings in Lisbon. I looked at some buildings in Spain, Madrid and Toledo. I looked at buildings in Lamu in Kenya, which is a coastal part of Kenya. I am currently looking at some buildings in India, in northern India. I've looked at southern India. And I've been looking at buildings in other parts of the world to talk about the idea that the way you measure sustainability really matters. Now, today in the US, one of the biggest things that people talk about sustainability is something called LEED. Now, LEED don't like me to say this, but a LEED building is not any better than building code building. That's the reality. We know that from data, whatever data they're using to measure, we can demonstrate that. So in particular, if you measure sustainability based on energy use intensity and focused only on that, then what happens is you'll be dealing with something called R-value measurements, which is heat transfer through conduction, and you'll be ignoring what you call thermolag or heat transfer through radiation or convection. I think that's where the error is. And a lot of building code that comes in from the national labs is pushing for energy performance through what we call energy simulation. I do energy simulation, and what I find through energy simulation is fundamentally that there's a flaw in the engine we use. It ignores a lot of things, and I think one of the things we need to do is begin to modify those. So anyway, let me go to India. So I'm talking about traditional buildings here. Traditional buildings are really designed from several things. Natural materials that come from the local area. Secondly, they have a very low environmental impact. So to produce CMU, you use way more energy compared to just cutting stone or using brick. Also, traditional architectural buildings come from what we call application of passive methods, adaptive methods. If you feel cold, you wear a sweater. If you feel warm, you remove the jacket. You don't turn the thermostat up or down. This is what you call about passive systems, very simple. And also, traditional buildings and historic buildings normally are used interchangeably because a lot of traditional buildings are very old, so therefore they're historic. But there can be new traditional buildings as well. The main difference in their construction is the morphology of those particular walls. So over there on your left, you see the typical construction of traditional walls, which are just thermal walls. There could be consistently one material. There could be also several materials, like the one on the left, on the right of the left group is actually walls on the outside and rubble in the middle. Lisbon is full of walls like that. On the right side is today's modern construction. We have other CMU with a gap in between. We put insulation and you put a facing on the outside. Or you can have a lightweight construction and then we put insulation inside it and then you put facing on the outside. This is typically how we do a lot of the buildings today. Now, I am glad that ASHRAE, which is what drove the air conditioning system, American Society of Heating, Refrigeration, and Air Conditioning, have come to understand and appreciate that, comfort is not just what you measure, but actually how you feel satisfied. So they have this PMV method for measuring. But also there's also the issue of indoor air quality, which talks about the range of temperature and humidity that human beings actually find acceptable. Now, people like Didier and Braga and also Humphrey looked at work in India. They said, how come people in India seem to be just comfortable in extremely high temperature according to ASHRAE conditions? And they realized that there's a slight gap in how those models work if you look at it mathematically. If you look at the lines that you see there, the range of thermal comfort is given by that gap in the middle. That is what we call thermal comfort. And actually, the one that is actually green is buildings that are air conditioned. So you look at air conditioning, the sensitivity to both temperature and humidity, compared to the blue one, which is a naturally ventilated building, where you can actually accept something much higher humidity and much higher temperature. Here in Charleston, it's humid. In the summer, with a porch and a fan, you can actually accept a slightly higher humidity and higher temperature compared to if you live somewhere else in an air-conditioned building. So energy performance of buildings here looks at the idea of estimating performance of a typical wall. And the big change that we have here is that as we measure existing buildings compared to what's assigned, we find there's a very big value gap between what is published of the material behavior and actual material behavior, which means, should we trust the value they give us for those performances? There's a gap there because not just the material, but a material and combination of other things. So if you're using CMU, for example, or brick, they're giving you a value of brick. They don't add what you use to connect the brick together. They don't add how you connect them together. And that's why there's a lot of faults in this calculation there. So here's an example of different materials here. So let's look at, say, for example, highlighted number 9 there. Paper number 9 looked at thermoplaster, thermoblock, and plaster. The thickness is about 0.45 millimeters, which is about 1.5 feet. The estimated value based on what you can look at assigned value is about 0.32 watts per meter squared Kelvin. But actually, when you measure this, it's actually 0.56 So there's a lot more transmission going through than actually what is being given. So there's already a gap there. If you look at, say, plaster hollow clay block, the value which is estimated is 0.42 to 1.5. And when you go and measure it, it's actually much lower. So traditional buildings now being assigned a lower value than actually what it is. Gypsum rammed earth, estimated value given 1.58. Measured value 0.35, very low transmission. And therefore, traditional buildings are not being given the correct assignment based on what is actually measured. So a fundamental way in which we measure these things is very simple. We look at heat flux. We put a sensor on the outside, sensor on the inside, and we measure the temperature differentials. One of the things that we don't quite do with the instruments we use today is to measure how much energy is absorbed in that particular wall and then radiated. So I currently have a PhD student from University of New Mexico who's grappling with this because he's finding that adobe buildings in New Mexico seem to be having a very high U value, especially when the sun goes down, because the sensor on the outside is radiating the heat, and therefore it's telling it that there's actually heat loss of the building. When actually in reality, what it's doing is radiating what it had absorbed, which has not gone on the inside. And therefore we're looking at how can we find a way of calculating this and add this to the system to make sure that we can correct this value there. So in India, we looked at Gutu buildings. There's several of them in India. There are about 324 of them. We just looked at only 4 buildings in particular. And these buildings, they reflect the local character in southern India. They're in Mangalore. And they're typically courtyard housing, mainly because of the place is hot and humid. Courtyard also because of culture. There's a different level of different groupings of people who can access the house. Therefore, the building actually is layered for different reasons. So here's examples of some of the Gutu houses. Very simple. They're very large, but can be designed for very small buildings. And traditionally, what you see here is a courtyard in yellow. The front is a porch, and then the rooms surround the building, 1 layer thick, sometimes 2 layers thick, but they have natural ventilations right through them. And what we did was we put sensors through the courtyard to measure the local temperatures, a weather station. We put sensors to measure indoor air quality in terms of temperature, humidity, and lighting in different locations. And then we put a U-value green tag to measure the U-value of those particular walls in 2 locations. And what we came up with at different times of the year, we measured this over the summer and over the winter. And we found out that if you were to use ASHRAE air-conditioned buildings, and basically what you're seeing here is that because the building actually has thermal mass, most of the temperatures are falling within what you call thermal comfort. If it was air-conditioned, then you're forced to air-condition that area because they're saying, oh, it's out of the range. But in reality, they're very, very comfortable. The other thing that we see here is that if we go and look at a model done by Olgay did this model in 1963. It's quite an old model. And what he did, looking at buildings in Iran, buildings in Turkey. Olgay was from Turkey when he came to the US to do his PhD. So he looked at these particular areas here and he said, one of the most interesting things in comfort is that if you have wind flow, air movement, then you can actually be more comfortable than at a higher temperature. So if you look at the range of temperatures in India, for example, over the summer were actually quite high outside the gray area of thermal comfort. But because there's air movement, you can tolerate that amount of heat. And that's why when you come down to Charleston in the summer and you walk out of the building, out of the hotel, you start going like this. You're actually increasing airspeed across there. That's what this is doing. And that's why buildings in the South are adapted to have porches and have natural ventilation. And adopted such that there's actually airflow, natural airflow that occur through the courtyard. And that's why you are able to stay in those higher temperatures, which LEED doesn't consider. They will not say, they'll say, no. You are out of the range, you need to provide air conditioning. Get the most efficient air conditioning system to make you comfortable. And I want to just thank David for inviting me, thank ICA, but also thank University of Notre Dame that gave me the money to look at this work, my colleagues at BMS School of Architecture, I thank them as well because I don't speak Marathi or Kannada. So with them, we're able to do the research. And School of Architecture, Dean of Architecture also providing the money for me to travel as well. So thank you very much. And if you have any questions, we'll discuss that.
Hi, my name is Patricia Andrasik, and David introduced me. I'm here from Washington, D.C. I'm a professor of architecture at the Catholic University of America. I teach mainly building performance analytics, so I'm extremely excited to talk with my previous colleague because I have a lot of questions and maybe some disagreements on some things. But I'm very honored to be here. Thank you so much. Really what I'm going to be talking about today before we get into our discussion, I'm a little mindful of the time. I want to talk about the steps to net zero design. What is it? And I want to talk about two main things, passive strategies and renewable strategies. And I have some graphs that maybe if you'd like, you can take a picture of to help you design net zero housing, focusing on passive strategies before you get into anything active. And then the methodology of the design process. And I grabbed a couple of students' projects today so you can see how a new traditional building is starting to be designed at Catholic University with some of the methods that I'm explaining to you. So as David has mentioned, this panel discussion aims to identify some appropriate metrics for sustainable architecture and discuss some of their challenges to adoption, but I'd like to offer some opportunities for adoption, rather. I was asked by David to be a part of this panel after we had a few phone conversations and about sustainable design and how the overly complex scientific and mechanical advances sometimes scares a lot of architects. It scares them away from exploring the depths of how their buildings can be designed not to lead or to the new net zero codes, but simply more efficiently utilized using resources. And believe it or not, just common sense, because that's really what sustainability is. Questioning the vernacular of sustainable design is very important. So just really quickly, how many of you have heard of or understand net zero design? Zero design. How many of you actually apply net zero focus in your projects? Okay, that's great. I have some questions here, and we can skip through those because at the end of this presentation, perhaps we can go back and we can get your opinion on these questions. In 2012, 60 buildings or projects were net zero energy or were emerging to that level. In 2018, 482 buildings or projects were net zero or emerging to that level. And in 2022, 757 buildings. So that's a really significant jump to net zero buildings, and it's exponential. It's only going to be increasing. Buildings are required now to be not just sustainable, but to produce as much energy as they consume, which is what net zero is. In 1997, 3 years before the U.S. Green Building Council's LEED rating system appeared, COTI, the Committee on the Environment, AA's Committee on the Environment, launched the annual Top 10 Awards in order to demonstrate best practices in sustainable design. My former colleague, Lance Hosey, prior to his death, wrote an excellent article that I often assign to my students, which describes how sustainable projects do not need to be ugly but do need to be new, no older than 3.5 years old in order to actually be considered for AIA COTI. But fortunately, after Lance Hosey's article came out, that was changed. A year later, AIA revised their criteria of the awards, and now the AIA's design excellence framework embraces older projects. In fact, if an older project demonstrates excellence in design and performance by today's standards, that's all the better. So what does that look like for a traditional or classical building? Well, let's explore. My background is architecture, and this is my first built construction. It is a sustainable building. It is a recycled building. And this is where I started my passion for sustainable architecture. I didn't have any metrics to it, but it was net zero. It produced as much energy as it consumed, and it was recyclable and demountable. So understanding how traditional, classical, or modern building can achieve net zero design, and even net zero water, and even net zero carbon, requires us to delve into what is net zero design and how do you apply it. So I've broken it down to a couple of different steps. These are 2 different steps, and this is all you need to design net zero buildings. You need passive strategies first, and then you focus on the renewable strategies. David scolded me for my previous presentation. He said it was too technical, so I put some more pictures and case studies in this presentation. But after we saw the previous presentation, I thought I could have just kept my presentation. In net zero design, 2 steps, passive and renewable. This is the most important. Does that make sense? Passive systems and then renewable. You don't think about PVs. You don't think about wind turbines. You don't think about RECs, nothing, until you have passively optimized the building. And that's where a lot of architects fall, unfortunately. So here are some examples of exemplary passive building design strategies to minimize resources. These are simple. This is in my last book, Heating, Cooling, Lighting, which if you're taking the licensing exam soon, it's one of the requirements for AIA, the Heating, Cooling, Lighting publication that I co-authored with Norbert Lechner. And these are some passive strategies. Passive heating. Wind, just like my previous colleague mentioned in this presentation. A solar chimney, which is basically a natural way of exhausting heat and providing ventilation. And of course, behavioral strategies are a part of passive strategies also, and the sweater is a very important part of passive design. If your set points in your HVACs don't have to be so extreme, and if you're not depending on your HVAC for the panacea to your LEED certification, then the sweater is a very viable architectural strategy. Also, controls, giving occupants controls for thermal comfort, very important. Let's look at what this looks like in an actual case study. Let's take the Michigan State Capitol, and one of my very good colleagues, an excellent engineer by the name of Hala Abudab from Loring Engineers, was in this building recently because Loring was awarded and won many awards thus far for doing the HVAC upgrades to this building. But interestingly, what we discovered in this expedition is that the building was already passively designed. If you notice the middle photograph, those are heating coils, and the heating coils are in the areas on the floor plan that are green. Those heating coils do not heat the building. However, what they do is they are the catalyst for the temperature differential that fosters ventilation. So this is a very simple passive design strategy for air conditioning, bringing in the coolth that's necessary to cool the building through heating coils that create the temperature delta, which moves heat upward. The second part of net zero design is renewable systems. So after we've passively optimized a building, and I'm going to give you more case studies of that, now we get into the renewables. We get into the do we use PVs, depending on your region. What do we do for renewables? And also, your active systems, lights, HVAC, but that's at the end of the design, not at the beginning of the design. We don't even think about those things. You know why? Because the passive design has the ability to decrease energy consumption over 50% of a building if it's done well, early, and thoroughly. Let's take a look at another building from my hometown, DC, by our friend James Renwick, which was remodeled, but this was remodeled to net zero standards. And this is the most interesting thing about this project. So when the building was built, and actually into the 60s, Jacqueline Kennedy was walking by with actually the director of the GSA. And she said, "What a delightful building." And he said, "Oh, it's going to be torn down, unfortunately." And she said, "Who would author something like that?" And he said, "Actually, your husband." And she said, "I think I have a sway in changing his mind." And she did. And since then, the building has been renovated, and recently it has been renovated to be net zero. And I'm interested to show you the passive strategies that went behind that. So the main corridor, the main hallway in this beautiful building was not really designed, was not really planned by previous architects to remain so beautiful. The initial feasibility study in 2010 proposed raising the building's roof, original roof, and lowering the basement slab and basically doing a lot of architectural modifications which would compromise the historical nature, claiming that the only way we can make this sustainable is by putting in more efficient HVAC, which would mean increasing floor-to-floor slab. But the winning engineers had another idea, and I'm plugging all these engineers. Roger Chang, who is now with Bruno Happold, was the architect under DLR in this project. These engineers started with passive strategies to drop the baseline energy requirements in the first place, then adopted to the standards of ASHRAE 34 in 2019, which were the energy guidelines for historical buildings, even before that reference standard became a requirement. Some of the features of this renovation were upgraded roof insulation, upgraded windows as passive strategies, and the removal of the existing lowered ceiling previously installed, which you can see on the left, to house antiquated fixtures. The lighting fixtures were passive strategies used to facilitate energy reduction. More specifically, the team targeted a reduction of 50% in the overall energy, a really significant reduction from the current codes, which was ASHRAE 90.1, 2007. So to meet these goals, after these and other passive design strategies were implemented, the project team worked with an LED lighting expert to custom make LEDs as a part of the active systems. This reduced lighting power density from 6 watts per square foot to 1 watt per square foot, which is really significant when you calculate how much lighting a museum uses. Synergizing with the energy reduction, additional passive strategies were applied to yield a total 35% reduction in not just energy, but in water use as well. How did we reduce water in a historical building? We replaced the initial radiant heating, which was water-based, which wasn't good for a museum in the first place. And instead of throwing away the condensate from the HVAC, which is a typically wasted byproduct, the engineers recycled it by sending it up to the cooling tower. And this cooling coil condensate reclamation actually saved 100,000 gallons of drinkable potable water, which is equivalent to about 2/3 of the water being used for the interior plumbing fixtures. So as a result, the integration of low-hanging fruit of passive strategies prior to the implementation of renewables or top-line active systems, this building achieves a 50-year overall life cycle before needing major renovations and has been rated a Class D net zero energy building. And of course, these projects are AAA COTE winners. One more fast example of exemplary net zero design using the premise of passive optimization like we discussed is the Wayne Espinal Federal Building Courthouse. There was a design build approach to this project, and it was responsive to the then government's requirement of carbon neutrality by 2030. The most basic behavioral strategy was the creation of a tenant guide that simply provided a list of preferred equipment including laptops and Energy Star labeled devices. And it allowed the occupants' behavior to be monitored so it can be then adjusted and so they can provide feedback. Design decisions include a 32-well geothermal exchange, which is a passive strategy. You're probably thinking, how is that a passive strategy? It's a passive strategy because it's not actually using any kind of energy. It's passively heating or cooling water to be preheated or pre-cooled before introducing it into the HVAC system. Inside, main strategies include prioritizing daylighting by removing the second and third floor ceiling zones with building surfaces that were previously flanking the perimeter. These removed and installed inside, as you can see in the hallway. Active strategies include daylighting sensors, and the lighting was absolutely upgraded to LED standards with wireless controls and integrated with the HVAC as the final active strategy. This passive-active synergy in this project can be nicely seen as all perimeter zones include design features to allow for a balance of energy efficiency and visual comfort, and I think beauty. A little bit more detail on the inside, the passive design of the envelope upgrades dramatically increased energy efficiency by adding high insulation without compromising the historical integrity of the building. Fenestration systems were also replaced, and there was an addition of very R-value intense rigid insulation. You're probably thinking, oh, here we go, Patricia. Here are the renewable strategies, and this ruins the building. Actually not. The PV array that was put on after the passive optimization was so small that when you stand from the bottom of the building, you're not able to see it. So it's actually hidden. This got the building to net zero. It's a 123 kilowatt photovoltaic array which generates electricity to power several 15 houses. And so, as I mentioned, net zero design is becoming a requirement. The idea of passive and renewable active strategies is integrated into the design methodology that's needed to design any building, whether it's classic, modern, or traditional. There's software that's involved. And this slide, you can take a picture if you'd like, so you can see the software that we use. Very simply learned, not engineering-based software, but very simply to arrive at the passive optimization before we start calculating how many PVs we need. I'm going to run through the last couple of slides. These are my students' projects, and this is what we're doing at Catholic. This is a traditional building by one of my students, Liam Maxim. He started off with a box, ran it through some simulations of what target EUI he needs. Then we started looking at carbon. We started looking at materials. And one fact, the graph on the top is a concrete mass option. The option on below that is a straw bale option. The building looks the same. And this is what it looks like. And these are the Sustainable Synergy Board, which explains to clients, future clients, what all of the strategies are in the building to get it to net zero. And of course, I'll conclude with a plug for our Master of Science in Net Zero Design program, which is not required to be modern, traditional, or classical. We use everything integrated. And one of my students just won the AA COTI 2023 Top 10 competition with her thesis project, Net Zero. Thank you so much.
Thank you, Patricia, John, and Steve. Let's see if we can have a moment for questions. If anyone has popped up.
I can also hand around the microphone for any questions.
Yeah, no problem.
Do any of you have a recommendation for a tool that I can use as an individual to measure my carbon footprint and do you have a recommendation for a trustworthy offsetting, like offsets, basically? Like, where should we go to, you know, please help me take care of my sins?
Who is okay? The very simple tool is called TallyCat, CAT, TallyCat. It's a free downloadable software that's an easy plugin on any type of Revit base. And how many of you are using Revit in your, a few of you, AutoCAD? AutoCAD, majority AutoCAD. Okay, so AutoCAD can be exported into, you can use the software with AutoCAD as well in the 3D form of AutoCAD. But it's a very simple downloadable program, and it captures carbon footprint very fast in the passive, in the schematic design phase of an architectural project. Yep.
It's okay.
Go ahead.
Okay. How do you see AI propelling authentic sustainability? How can we use it in this world, please?
AI is a controversial thing. And AI can be, AI is about data, really, and speed of data. So it can be used correctly, or it can be used to mislead people. So you can actually use AI to do things for you. So for example, with AI, I can look through a database of different buildings that have been done before. Say, for example, in the state of New York, they have all the data of energy performance of all the buildings. I can run through that very quickly and know what's the optimum based on the consumption and the footprint. I can use that very quickly. So it's how you use AI. I think that's the key thing. Now, the challenge we have now is that we still don't have policies on how to address them. And therefore, we are likely to have problems in dealing with AI correctly. Most universities are still grappling with it. I mean, I'm in a committee at the Faculty Senate where we're discussing this, and my colleagues from science are saying, we use AI all the time. In architecture, we're saying we want to touch it because we don't know what to do with it. But I think AI is coming, and we just have to control it very carefully.
The low-hanging. The low-hanging fruit of all sustainability decisions is actually conditioning people to make different choices because because they see it as a better choice for them. It is not what is what gets delivered by a machine. It is a fraction of the benefit of what happens when the humans behave better. So I'm not saying there's no value to AI. We don't actually know what it's going to be, but I do know that the most important thing is to reach the people as opposed to reach for the machines first.
Well, thank you so much to our speakers. David, sorry, last few words.
Oh, just thanks to the audience for your interest, and thanks for the panelists for putting up with me this past few months and putting the presentations together. And again, thanks to the ICAA for your support in this sustainability initiative. Thank you, everyone.
Thank you.